context here is what's called Euclidean quantum field theory. And the basic is that you give yourself some action functional, and you think of this as, you should think of this as coming from a field theory. And the easiest action functional you can think of, right? So a functional, it's a function of a function. Okay, so phi is itself a function here, the argument. And this action functional S takes a function as an input and spits out a number. And the sort of thing that you have in mind, right, the easiest example, and that's a very important example in this business, is the one that takes a function phi and spits out the L2 norm of the gradient of phi, so the integral of gradient phi squared. Okay, so the square of the L2 norm. Okay, so that's the running example if you want. And many other examples are somehow close to that one in spirit. Okay, so the sort of thing you should think of is that example. And then, given such an action functional, Euclidean quantum field theory boils down to building a measure on a space of functions, which formally is something like e to the minus that action functional times Lebesgue measure. Okay, that it's a Lebesgue measure on the space of functions. Now, so first there's a whole story about why this has something to do with real quantum field theory. And so that goes back to the 60s, and there are works by especially Ilya Chevyrev that kind of relate this to actual, real quantum. I'm not going to talk about that. So we are just going to take this as a starting point. Okay, so we are given one of these action functions, and we want to turn that into a measure. We want to sort of think of this action functional as being the logarithmic density of a measure, of a probability measure on the space of fields. Okay? And what's the problem with that? Well, the problem is that there's no Lebesgue measure on infinite dimensional space, right? So Lebesgue measure, we all know what it is. It's measuring things that's invariant by translations and so on. If you ask yourself if such a measure exists in an infinite dimensional space, then there's always something that goes wrong, right? I mean, you can get some of the axioms of what a measure is to be satisfied, but there's always one that's going to fail, right? So you cannot just take this expression sort of at face value, right? Because there is no Lebesgue measure. So one thing you can always do is that you somehow fix stuff by making it finite dimensional, right? I mean, like a space of a function, say on, I don't know, R2, I can always approximate it by, putting down the grid. Sort of instead of looking at the whole plane, I look at the chunk. And then on the chunk, instead of looking at it as a continuum, I just put a grid of points, and now I have finitely many points. And I just specify the value of the function at each point, and that's some kind of approximation. Okay? And then in many cases, so for example, in the example I gave you, well, the gradient might be replaced by some finite difference. And so now you have a sort of discrete action functional on a finite dimensional space, where you just take the sum of finite difference squares. And then you can take that expression here, and it actually makes sense for the finite dimensional case, and then you can ask yourself, does it have some sort of limit as you make the grid smaller and smaller, and maybe make the chunk on which you define the grid larger and larger. Okay, so that's the sort of standard way of doing. And of course, in order for this to work, it better be that S is sufficiently coercive. So coercive basically means that it grows in all directions, right? Because you would want this to be a probability measure, and so the least that you would want is that e to the minus beta is actually integral, right? So it should have, so S needs to grow so that e to the minus S decays. Now, the same sort of construction also shows up in statistical mechanics, but the example that I want to talk about today is the one where the action functional is what's called the Yang-Mills functional, and that one really just has the motivation that comes from quantum field theory. Okay. So now what is the Yang-Mills functional? So in this case,
instead of our field, right, instead of just being a function that takes values in the real numbers, what we do here is that you fix some compact Lie group, and that's going to play a role a bit later, but for the moment it's just, think of it as being, n times n of orthogonal matrices. Okay, just ON, for example, SON, for some fixed n, 3. Okay, so you take 3 by 3 matrices so that A transpose A gives you the identity, and then this has a Lie algebra, which is essentially the tangent space and of at the identity matrix. So that's a linear space. Okay, it's a finite dimensional linear space. And now your fields are actually one-forms, which you can kind of think of as vector fields, but except the principle is sort of dual. But if you think in coordinates, it's sort of like, if you're in R3, you have 3 components. And each component, instead of being real valued, it takes values in that Lie algebra. Okay? So instead of having one field, you have as many fields as the dimension of your space. And each field, instead of being real valued, it takes values in this Lie algebra that you fixed. Okay, but which is just a finite dimensional vector space at this point. And then the action functional in coordinates, it has this sort of this funny form here. So it's again an L2 norm squared of something, and that something is called the curvature tensor. And in coordinates, it's given like this, right? So my field now, I call it A. Right? So the A, it has components AJ. J goes from 1 to the dimension of your space. And each AJ takes values in that Lie algebra G. Okay? So these guys still take values in G, but then you take a norm. So on that Lie algebra G, there's a natural norm. So you take whatever the natural norm is. And you square this expression, and you also sum over the ij indices. And you have here some kind of a curl, and then you just have the Lie bracket between ai and aj. And the reason why this, where does this come from? I mean, you have some sort of random expression like that. And it's called the curvature tensor. Right? So in general, whenever, so maybe the curvature that you're also familiar with is the curvature in the differential geometry, right, in Riemannian geometry. So if you have a manifold, then there's a Riemannian curvature tensor there. But in general, you actually have a curvature tensor whenever you have something which is called a connection. So in the case of the manifold, the connection is the thing that tells you how tangent vectors move around. What's the natural way of moving around tangent vectors if you move along a curve in the manifold? Okay? So if you have a curve on your manifold, you take a tangent vector at the start of the curve, and then you sort of move around and you sort of glide in the most natural way. Then that's the Levi-Civita connection, which tells you, how your tangent vector moves as you move along the curve. And whenever you have any sort of notion of connection, there's a notion of curvature that comes with it. And in the case of the Riemannian manifold, that gives you the Riemann curvature tensor. Okay? Here, these A's, you should also think of them as a connection. And here they're a connection on the underlying space, which is just a torus or something, times that Lie group G that you fixed. Right? So you should think of, well, there's a space here, which is the torus times the Lie group. And now the connection tells you how to lift a curve on the torus onto a curve on this product space, which is torus times Lie group. Right? So if you, there's no chalk here. There is chalk. Cool. Okay, it's not going to show up on the YouTube stream, but never mind. So you should think of, right, so you have your torus. At each point, you attach sort of a copy of G, and then you take a curve here on the torus, and you want to lift it to a curve on this product space, right? So at each point of the curve, you have this copy of G attached. And now, of course, there's a natural way of lifting it, which is, if I start here, well, you just look at what's the difference between these 2 points, and you keep it to be the same, and that will be sort of like the horizontal way of lifting it like this. But that assumes that you kind of know which point of G here corresponds to the identity element. And what you should think of here in this business is that at every point you have a copy of G attached, but you've sort of forgotten about which element is the identity, right? So like if it's a circle, you don't distinguish any point on the circle. You don't specify, this point is actually like, if I think of the circle as being in the complex plane, this point is the number 1, somehow, which would be the identity, right? So you forget about which one's the identity. And then you don't have a canonical way of lifting this anymore, right? Because you don't know how you should do it. And so you have to actually specify a way of doing it. And now, one thing you can always do is you can arbitrarily fix one point on each of these fibers and sort of decree, well, that one is the identity, right? That gives you a way of lifting things, but that was completely arbitrary. And now if you have a different way of lifting it, well, the different way of lifting it would just tell you that, well, at every point, you have to say how it differs from the one that you fixed in some kind of arbitrary way. And that means that now at every point you have to specify in which direction you're kind of moving in the tangent space, right? And so it's sort of, so what sort of object is that? So whenever you're given some tangent vector down in the base space, you have to specify in which direction of that copy of G you're moving upstairs. So it's something that gets fed a tangent vector of the base space, and that spits out a tangent vector of G. And that's exactly a one form with values in the algebra, right? Because the algebra is the tangent space of G, and the one form is a thing that gets fed a vector as an input, and that spits out, well, a number for usual one forms, but in this case it spits out the tangent vector of G, okay? So in this case, this A, it really has an interpretation of connection, and if you take that interpretation, then there's a natural notion of curvature that comes with it, and if you do things in coordinates, well, that's the expression that it has. Right? Okay, so that's where this comes from. Now, the important thing here is, remember in that picture, well, okay, that's scribble here. But I'll try to explain sort of where this connection comes from. You have to kind of specify, you sort of make a non-canonical choice of somehow fixing one base point for each fiber, somehow, which you consider to be the identity element. And now this could have been completely arbitrary, right? You could have made a different choice, and it wouldn't change the story at all, provided that you change the A in the corresponding way that sort of undoes that choice, right? And so making a different choice corresponds to, at every point, choosing an element of G, right? So it's a function from the torus of G. So there's a group here, which is all the functions on the torus with values in G. And that group is some sort of like, it's a group of coordinate changes. You should think of it, right? Because it's like the group that allows you to specify one of these arbitrary choices, which is like the analogy with Riemannian geometry, it's like a choice of chart. Right? So if you do a change of chart here, in this particular case, a change of chart corresponds to take a function with values in that group G, and then at every point, move that base point by the amount that you've chosen at that point, okay? So that's like a change of coordinates, and if you do that change of coordinates, the A guy in the new coordinates has a different expression. And this formula tells you how the A transform under these changes of coordinates, right? And so now, since this curvature is supposed to be an intrinsic thing, it shouldn't depend on the choice of coordinate system. Okay? And so what happens here is that indeed this action here is invariant under this group action. Okay, so like this is action as in the sense of group action, and this action is action in the sense of action functional. It's not the same action. Anyway, so it has this big symmetry. Right? So there's this infinite dimensional symmetry. And now clearly that's some kind of a problem, right? Because it means that the function S is flat in infinitely many directions. Right? Because it has this infinite dimensional group under which it's invariant, and so it's constant on every orbit of that group. Right? But now, that basically destroys the thing we wanted to do on slide 1. Right? So we said, oh, we want to construct a measure which is e to the minus s times Lebesgue measure. If you have any Lebesgue measure doesn't exist in infinite dimensions, so you do approximations, pass to limit, whatever. But still, if S is constant on sort of infinite dimensional subspaces, right? Then, well, the thing that you get should look like the Lebesgue measure on these infinite dimensional subspaces on which it's constant. But the Lebesgue measure doesn't exist in any infinite dimensional space. Right? So there's no chance that something like that exists. So what do you do then? Well, in this particular case, all the physical observables, if you want, of your theory that you would be interested in, they are themselves functionals that are all invariant under the action of this gauge group. Right? So in some sense, you're only interested, instead of being interested on that measure, on the space of connections, you're actually only interested in the measure on the space of connections quotiented by the action of that gauge group. Right? Because if you want all your observables are actually constant on each gauge orbit anyway, and so you can just as well quotient by the action of the gauge group. Right? So you can just say, well, I have these infinite dimensional orbits, I just pretend that each orbit is a point. Right? So I get the sort of reduced space, which is the space of orbits. And so the kind of, here the Wilson loop, so that's sort of the example of the sort of action, the sort of functional which is invariant under these changes of coordinates, which is exactly something like you take a loop down on the torus, then you lift it to this torus times group. If you go around the loop, in general, the point where you end up once you've lifted it is not the same point as the one where you started, so you have a sort of difference between the two, which is an element of G. And if you now take any class function of G, then it turns out that, and you apply it to that element, it turns out that this is something which is invariant under the action of the gauge group. Right? So that's typically the kind of observables that people are interested in. And they only depend on the gauge orbit, not actually on the specific choice of connection within one of these orbits. Okay, so you only need to build the measure on this quotient space. So that has a better chance of working, right? Because now you would hope that this action functional, even though it's constant along the orbits, well, maybe it's sort of sufficiently coercive, it maybe grows sufficiently fast if you look at it in the space of orbits. Right? Sort of in a sort of transverse way. Still, I mean, this tells us that there's a non-zero chance of being able to do something, but it doesn't tell us how to do it. Right? Now, there's a whole bunch of people who have worked on this problem. Maybe the main one I want to mention is in 2 dimensions. It turns out that one can sort of guess, like you can look at some finite dimensional approximations of that problem, and you can look at these Wilson loop observables that I just mentioned on the previous slide, and now you give yourself, say 5 different loops. Under that measure, these Wilson loop observables are just random variables. Right? So then that just gives you like 5 real value random variables, and you want to determine the joint laws of all of these random variables. And in the 2-dimensional case, you can basically guess that joint law, because you can see what it is for finite dimensional approximations, and you can see that it actually converges to a limit. And so that's been studied, I think, in the math literature. It sort of started with works by Langros and Keynes and Gupta. And there's more recently, there's work by Thierry Lévy on this. So this is now pretty well understood in terms of somehow finite dimensional distributions of these Wilson loop observables. But that's very specific to 2 dimensions because you can basically guess the answer. Okay? In 3 dimensions, you can't guess the answer, or in 4 dimensions. And there is some previous work, especially work by Balaban in the 80s. So he has a very long series of works that he published during the 80s, which somehow suggests that this theory in 3 dimensions is renormalizable, and that you can somehow make sense of it. But it doesn't really give a good state space, and it doesn't really actually construct the measure. And there's a very recent work by Hao and Chatterjee from like last year, where they just build a candidate state space, because it's not even clear. So the thing is that these measures, they tend to end up living on very irregular fields. They tend to live on sort of distributional fields. So actually these measures, even in the simplest case, like the first case I told you, the e to the minus integral of gradient square. So that one is a quadratic thing, e to the minus something quadratic is Gaussian. So the measure you get is Gaussian. Gaussian measures make sense in infinite dimensions, so we sort of know how to define them. So that one, there's no problem at all defining it, so that's called the free field. And it turns out that already in 2 dimensions, the free field is not a random function, but it's a random distribution. And the higher the dimension, the less regular that distribution. Okay? And then it's not completely clear, right? Because when you have distributions, now it's not, in this whole story, if your connection ends up being a distribution, it's not even clear what that means. Then the action of that gauge group, it's not completely clear how to define it, and so on, right? So it's not obvious a priori of how to even define the objects that we're talking about before we even try to construct that measure. And so in that work by Hao and Chatterjee, they gave us a sort of candidate state space, if you want, that we would expect these things to live on. Now, the approach that we're following, something that was actually proposed by Parisi and Wu in the 80s. That Parisi is the Parisi who got the Nobel Prize a couple of years ago. Where what he said is, well, if you have a measure of that type, pretend that everything makes sense, everything is finite dimensional, say. Then you can look at this kind of noisy gradient flow, right? So you should think of like d phi by dt is minus gradient s of phi. So that's just the gradient flow that tries to find local minima of that action function on S. Plus some noise. So this guy is white noise. It's white noise in time that takes values in whatever space of fields you're looking at. And the covariance in the space of field has to be somehow compatible with the metric structure that you're using to define that gradient somehow. Then if you look at that equation, the solutions have the property that if you start with basically any initial condition, say deterministic, say you start at 0 or something, and then you run it, then the solution is something random, because it's, you solve an ODE, but with some random noise term on the right-hand side. So the solution is random as well. Then the law of that random variable, as time gets large, actually converges precisely to this measure here, normalized to be a probability measure. Okay? So that's something one can just check in finite dimensions. And so then in infinite dimensions, you can sort of turn the problem on its head. You can sort of define this measure as being the law that you get by running that guy for a long time. Right? If it has a limit, then you just say, well, then that's what my measure is. Right? In finite dimensions, it's the same thing. And so in infinite dimension, well, one of them I don't know how to define it. If I know how to define it, the other one, then, well, I can just postulate that they're the same. Right? That's what you usually do anyway. So the hope here then is that, well, maybe this dynamic is easier to construct than the measure itself. Okay? So then maybe you should actually study the dynamic instead of directly constructing the measure. And then you just define the measure as being the, what's called invariant measure or steady state or whatever you want to call it for your dynamic. So if you do that for Young Mills, you get, right, so now your field is a space of fields, so it's some infinite dimensional thing. So this equation is not an ODE with noise, but it's a PDE with noise. Right? So a radiant flow in a space of functions is typically a PDE. And if you look at the PDE that you get, you find something like this. It doesn't really matter too much what these terms are, but it's basically of this form if you write it in coordinates. Right? So there's like a heat equation thing, but then there's this extra term here, and then there are lower order or higher order, depending on how you count terms. So what I mean lower order here is because they involve less spatial derivatives. Right? So there are these two terms that have second derivatives in space, and all the others have just first derivatives or low derivatives. Now, that equation is already problematic because it's not parabolic. Right? So like the heat equation is something really nice that we like because it has very nice smoothing properties, very nicely behaved. That term here destroys the fact that the Laplacian is parabolic, it just sort of cancels it out. But again, so here there's a trick, which is that we can remember, since at the end of the day, we're only interested in constructing this measure on this quotient space. Right? We're not actually interested in constructing the measure on the space of connections, but only on the space of connections modulo gauge orbits. So if you think of, so here this is a cartoon where the board is the space of all connections, and these lines are sort of the gauge orbits. So if you take a connection here, then all the connections that are on that line are the ones that you get from this one by coordinate change. Right? So you take an element of this gauge group G and you act on it, on this connection here with it, and you get this whole line here that are sort of physically the same, just written in different coordinates. And then, so say everything makes sense. Then if I start from here, I would get some sort of random evolution. And that random evolution would have the property just because of somehow the invariance of the action functional and sort of the invariance of that noise and so on. So at least formally, what you would expect that thing, if it did make sense, you would expect it to have the property that if I start from this different point here on the same orbit, and I run this guy, then the solution you get here after time t is the same as the solution you got for this guy, just acted upon with the element g. Right? So that there's sort of like this commute, whether you first act with g on the initial data and then you run the solution, it's the same as first running the solution and then acting with g on the end result. Okay? Now, that suggests that actually at every point in time, I could sort of move a little bit along the orbit g, along the orbit at that point. And that doesn't really change anything as far as the quotient dynamics is concerned. Right? Because as far as the quotient is concerned, starting from here or starting from here, that's the same initial data if you want. Right? But so I can even, like halfway through, so since when I'm at that time here, I could just move a little bit in this direction of the orbit and then continue from there. Again, it would give me exactly the same dynamic as far as I look at only the quotient. Right? And if you do the calculation, well, what the Turk found, the Turk found in the context of Ricci flow, which is a bit different, but there's a similar sort of problem where changes of coordinates are actual changes of coordinates. And Donaldson then in the 80s sort of figured that the same trick works here. So what they said is, well, exactly what I just tried to explain. And then you have to choose sort of in which way you sort of push along the orbits. And it turns out that basically you can take any functional h of your field, of your connection, and then you take this sort of covariant differential of that. Then adding anything of that type to the right-hand side of your equation essentially corresponds to doing one of these pushes, but in an infinitesimal way, somehow in the direction of the orbit, right? And so it shouldn't change anything as far as the quotient dynamics is concerned. And if you make the right choice, then you can cancel out that term, and you can make it actually parabolic, the equation. Okay. Right, so the trick now is you do this, the third trick, the third Donaldson trick, and so now you manage to, at the end of the day, turn this equation into actually a nice parabolic equation, with there's some quadratic nonlinearity in A and its first order derivative, and there's a cubic nonlinearity in A, and then there's this noise, which now is space-time white noise, so it's sort of like independent random variables at every point in space-time. Okay, now for equations of that type, there we now have a sort of a black box that allows to give a meaning to it. Right? So it's still not clear what the equation means, because, as I mentioned earlier, solutions are going to be distribution valued. They're going to look roughly like this free field that I mentioned earlier, which is a distribution, and especially in dimension 3, it's sort of a pretty irregular distribution. And so then here you have to take like cubic functionals of a distribution or quadratic things of a distribution and its derivatives. So it's not clear how to define these things. You're not allowed to cube a distribution in general. Right? But still, so by now we have a sort of theory which tells us basically, if you smooth out the noise and then sort of remove the modifier, then you can pass to the limit, provided that you actually add something like what we call a counter term, to, in some sense, cancel out some kind of resonances. Right? So there might be some sort of resonances showing up, so things kind of want to blow up. And you have to modify the equation in order to prevent these blow-ups. So in this particular case, if you do the calculation, it tells you that you have to remove a term of this type for some large constant c. So you have to sort of change the equation and remove this kind of linear term. And then the theory tells you, okay, so there's a limit. You can pass to the limit as epsilon goes to 0, and there's a limiting guy. Now, on the one thing, you think you're happy. So, okay, so I've constructed the dynamic, and so my measure now is sort of the invariant measure for that dynamic. On the other hand, you're not happy because for two reasons. The first reason is that this is no longer canonical because I have to subtract this term, but then I have to make a choice for this constant. Now, the theory gives me some sort of explicit formula for that. Okay, and that's going to blow up as epsilon goes to 0, and especially in 3 dimensions, it's going to blow up like 1 over epsilon or something. And there's a log epsilon term as well. And then, okay, so you plug in the constant that the theory gives you, and there's a limit. But now I could plug in that constant plus 5, and it will also get a limit. I will get a different limit. Right? So I can sort of add any fixed number to that constant, then I would still get a limit, I just get a different limit. So it means that here I don't have one solution theory, but I have like a one-parameter family of solution theories, which is sort of parameterized by the finite part of that constant. And they are a priori, they will have different invariant measures, so which one's the right one? It's not clear. The other thing is that, this equation has this kind of gauge equivariance, which is that if you start at a different point on the same orbit, you basically get the same solution, at least modulo, again, quotienting by the action of the gauge group. That's sort of a very specific property of that specific choice of nonlinear equation. I mean, here I didn't really write down what these bilinear and trilinear terms are. But if you take an arbitrary one, it's not going to have that property, right? There's basically only one choice that gives you that property. So if you now suddenly add a term like that, that property is going to break. Okay. On the other hand, turning this white noise into a noise that's not white anymore by sort of smoothing it out is also going to break that property. So you've broken it in two different ways. Now, if you believe in miracles, then the two different ways of breaking it might just cancel out, and so that in the end you don't break it, right? And okay, so that's the result, basically. Okay. So the result is that miracles happen. And so in two dimensions, we have a sort of really nice setup. Basically, we can really find a space of distributional connections on which you can define this dynamic, and you have to be careful about how you define distributional connections. And like now your gauge group, it's not arbitrary functions with values in G, but it's like Hölder functions with a specific exponent that depends on which choice of distributional space of connections you take and so on. Right? But you can basically, the theorem, you can choose all these things in a super nice way, so that you get a nice space of orbits on which you can do probability theory. And the important part here is this uniqueness thing, right? Is that actually among this one parameter family of solution theories, there's exactly one that has this gauge invariance property, right? So there is exactly one guy that has this gauge invariance property, and so that's the right one. Okay? And actually, a posteriori, so there's a very recent result by Ilya and Hao, where they now actually connected it directly to what was already known in two dimensions. Okay, so in two dimensions, remember I told you that in some sense we already knew what the measure is because one can guess the sort of finite, the joint distribution of finitely many Wilson loop observables. And so what Hao and Ilya did is that they showed that, well, you can look at lattice gauge theories, which is sort of one specific kind of way of discretizing these things that preserves the geometry. And if you do that in two dimensions for pretty much any discrete version of the action functional, if you let the lattice spacing go to zero, the limiting process is the same as the one that we constructed. Okay? And so in particular, that process has a unique invariant measure, and that unique invariant measure has precisely the finite loop distributions that were predicted early on. Okay? So it kind of, the whole thing sort of completes, goes around the circle in nice ways. We have some result in 3 dimensions. The situation is much less nice and less complete because things get more singular. So we can still build a state space. We have a similar kind of result, but the state space is not as nice. It's not such a sort of nice space from a probability theory point of view. And the other thing is that we don't, in 3-dimension, we don't a priori have a guess of what this Young-Mills measure is. The point was to actually construct it. The problem is that the dynamic that we construct, we can only show that it has like, maximal solutions in time, but they might blow up in finite time. So we have a notion of maximal solution, but we don't know that the maximal existence time is actually infinite. Right? So that's, I guess, one of the main problems in 3 dimensions. But what still has, even in 3 dimensions, one still has this kind of uniqueness result, which in 2 dimensions actually comes out of explicit calculations. In 3 dimensions, you can't do the explicit calculation, and you have to come up with a sort of difference of nice argument. But I think I sort of should probably stop here, so I leave a few questions here. And thank you very much.